I'm so glad you came back to do lesson 6.2 supplement. This is actually part 2. Remember in part 1 we talked about the derivatives of these arcsine, arccos, all those functions? Well, remember integration is the opposite of derivatives. And so if I had this format where this is very similar to what, 1 over root 1 minus x squared, remember that? Well, I think in our 6.2 notes we stated that this was equivalent to arcsine of u over a plus c, and the one on the right is very similar to the arctangent one, arctangent of u over a, but don't forget this one has an extra factor of 1 over a in front, plus c. I think if you want me to prove it, either it's in the notes from before or I'll just do it in class with you. But anyways, these are not formulas that I just pulled out of the hat. There's proofs for it. Okay? But for this lesson, I want us to be able to apply these formulas, because you may get questions where it may be hard to see if you have a sum of squares in the denominator, which is the arctangent one, or the square root of a difference of squares, which is the arcsine one. Okay? By the way, we don't use arc cosine because it's just really the negative of arcsine, so we don't have to worry about that one. But you do need to do some manipulation to see the square. So how do we do that? Remember from pre-calculus 11, the idea of completing the square. Remember how we had to do that to change into vertex form? Well, here's another application of it to change it into squares. So if you look at number 1a, I don't know if you remember, but we did something like this. We said, okay, let's separate it. What magic number gets to be plugged in here to make these three things a perfect square? And I don't know if you remember, but it's always half of the coefficient in the linear term. So half of 4 is 2, and then we got to square it. That's plus 4. But wait, we can't just blindly add in 4. That changes the whole value of the equation. So we have to balance it out by subtracting 4. Now, these three terms here, and the lovely trinomial, that now becomes 1 over x plus 2 all squared. And then now 8 minus 4, of course, is just plus 4. By the way, I forgot this dx in there. Why is this handy? Well, doesn't this look like the arctangent one? I have a squared plus 2. Can you not see that a now equals to 2? And the u is the same thing as x plus 2. And then we should double check what is u prime. Well, the derivative of x plus 2 is just 1. That works because that's the numerator. So knowing this, we can just say, hey, by that formula, we get the answer 1 over a, which is 1/2. Arctangent of u, which is x plus 2, all over a, which is 2, and then plus c. Look, we're done. So as long as we can match up the form, we can then plug it in and get the answer right away. Okay, part B, same idea. This time now I have a 2 in front, so I don't need to remember we have to factor out the 2 first. And then ask yourself, what magic number goes there? I hope you said half of negative 6 is negative 3, all squared is 9. To balance it out, we subtract 9. And if you said that, I say no! Remember, there's a 2 in front that gets multiplied in, so you didn't actually put in 9, but you put in 2 groups of 9, which is 18, so to balance it out, you must also subtract 2 groups of 9, which is 18. Tricky. So now this becomes 1 over 2, bracket x minus 3 all squared. 26 minus 18 is, of course, plus 8 dx. And you're like, this doesn't look like any of them. Okay, fair enough, fair enough, fair enough. But look, the denominator, I can factor out a half, or 2, and that leaves me with x minus 3 squared. 8 divided by 2 is 4, and now we are in business! Because now I hope you can see that u equals to x minus 3. U prime equals to 1, that's great, and then a equals to 2, so here we go, we still have the 1/2, but it's 1 over a, arctangent of x minus 3 all over a plus c. Okay, and then if you really want to simplify, 1/2 times 1/2, that's just a quarter, so 1/4 arctangent, or you can write down inverse tan this time, just so I can spice things up. done. And I should put my equal signs here. I forgot my equal signs here as well. Alright. Last but not least. Ooh, 1 with the square root, so you know this is going to be arcsine, right? Alright. Now, the tricky part about this one here is I'm going to actually rearrange this first. I don't like having the x squared at the end. I don't like having it a negative in front either, so I'm going to actually factor out the negative. Okay. And then I'm going to leave the 21 over there on the outside, like this. Once again, what's that lovely magic number? Half of 4 is 2. 2 squared is 4. Notice I didn't put in positive 4. I put in negative 1 times 4, which is a group of negative 4. So to balance it out, I have to have a positive 4 here. Okay? Tricky. Negative x plus 2 all squared. 21 plus 4 is 25 dx. If you want to write it like this, which might look a little bit nicer, 25 minus x plus 2 squared dx, that's perfectly fine. Now I hope you can see that the a value is 5, the u is just x plus 2, and once again u prime is still 1. We're in good shape, therefore this is just equal to the arcsine of u, x plus 2 over 5, which is the a value, and don't forget plus c. There you have it. Using this idea of completing the square to transform the denominator into either the sum of squares or the square root of a difference of squares, and then just go ahead and apply the formula for arcsine or arctangent. Bam! You're done. Now, there is another type of skill you might need to know, and that's when you're integrating a fraction where the degree of the numerator is, that's right, bigger or equal to the degree of the denominator. Once again, you're going to have to use stuff you learned from pre-calculus days. This time it's long division from pre-calculus 12. Oh, you're like, no way. Integrating this, notice the highest degree in the numerator is a 2. The highest degree in the denominator is also 2. So, if I were to do some long division, let's see what happens. You're going to ask yourself, x squared times what gives you x squared? Yeah, they're one of them. 1 times x squared is x squared, 1 times 2 is 2. I'm going to line them up, and then like I do long division, we're going to subtract. X squared minus x squared is 0. Negative 4x minus 0 is negative 4x. 2 minus 2 is 0. Hooray! Why? Because now this integral is the same thing as the quotient, 1, plus the remainder, which is negative 4x all over x squared plus 2. Okay? And you're like, why does this help? Well, I can separate into 1 dx minus, I guess, integral 4x over x squared plus 2 dx. Why is this helpful? Well, I hope you can see that the antiderivative of 1 is just x. Yeah. But the other one here, not so easy. Yet still doable. Because I hope you can see that the denominator is a squared term. The numerator is a linear term. This is a very typical question where it should be yes. Use substitution of the denominator. Why? Because if I now do du dx, I get 2x, which is great, because that now is something similar to what I see in the numerator. If I were to solve for dx, I guess you can get du equals to 2x dx, dx equals to du over 2x. Let's make the substitutions. Here we go. 4x over u, and dx now becomes du over 2x. Perfect. That just simplifies to 2. Oh, the integral of 1 over u. Yeah, natural log of the absolute value of u. By the way, don't forget you still have this x in front. I should copy that down as well. And then also don't forget this is an indefinite integral, so don't forget plus c. And then finally, don't forget that you didn't start with u, you started with x. So you should replace u with x squared plus 2. And that would be the correct answer. Just a little note here. You didn't really need the absolute value here because x squared plus 2 is always going to be guaranteed to be positive. So if you did curve brackets here, you'd still be fine. But just to be safe, I like the absolute value. Alright? You need some practice on this. And I gave you some practice. Look, right here. Do them. Please. Please. Please do them. And then look for the solutions.